In automotive coating systems, dry film thickness, DFT, is not merely a dimensional parameter. It is a fundamental variable that governs solvent release, mechanical performance, appearance quality, and long-term durability. Even when formulation chemistry remains unchanged, variations in film build can shift a coating system from robust to failure-prone. From a film formation perspective, DFT directly influences solvent evaporation and diffusion pathways. Thicker films increase diffusion distance for residual solvents, slowing release during flash-off and bake. This raises the risk of solvent entrapment, blistering, and popping, particularly in primers and clear coats. Conversely, films that are too thin may lose solvent too rapidly, leading to poor leveling, increased porosity, and reduced film continuity. Mechanical properties are strongly thickness-dependent. Impact resistance, stone chip performance, and flexibility scale with film build up to an optimum range. Below minimum DFT, coatings lack sufficient energy absorption capacity, increasing crack initiation and chipping. Above maximum DFT, internal stresses accumulate during cure and cooling, raising the risk of cohesive cracking and delamination. Appearance outcomes are equally sensitive. In base coats, DFT variation alters metallic flake packing density and orientation distribution, affecting color strength, flop, and travel. In clear coats, excessive DFT increases orange peel and reduces DOI due to limited leveling and surface relaxation. Insufficient DFT reduces gloss uniformity and scratch resistance. At the process level, DFT variation arises from spray application parameters, gun overlap, atomization efficiency, and robot path accuracy. Differences between laboratory panels and full vehicle bodies amplify this effect. Flat panels receive uniform deposition, while vehicle geometries introduce edges, recesses, vertical surfaces, and variable airflow, all contributing to non-uniform film build. Thermal mass differences further complicate DFT behavior. Thicker body panels and reinforcements alter heat-up rates during bake, affecting solvent release and cross-linking kinetics. A DFT that performs well on lab panels may trap solvent or cure unevenly on production bodies. OEMs therefore specify tight DFT windows rather than target values. These windows represent a balance between appearance, durability, and process robustness. Coatings that perform only at nominal thickness, but fail at tolerance extremes pose unacceptable production risk. From an RD&I risk management perspective, DFT sensitivity is systematically evaluated during development. Formulations are tested at minimum, nominal, and maximum thickness to identify failure thresholds. Solvent balance, rheology, and cure chemistry are adjusted to widen the acceptable DFT window rather than optimize performance at a single point. In production, DFT control is a system responsibility involving formulation robustness, application process control, and measurement feedback. No downstream process can fully compensate for improper film build. In summary, dry film thickness variation fundamentally alters solvent release, mechanical behavior, appearance quality, and long-term durability. Understanding and controlling DFT sensitivity is essential for translating laboratory success into OEM-approved, production-stable coating systems. If you have technical questions related to DFT optimization, solvent popping at high build, thin film durability failures, or lab-to-line thickness mismatches, share them in the comments for discussion in future episodes.